Our next measure of variation is called the coefficient of variation. The coefficient of variation is specifically used to compare data with different units. So just like standard deviation and variance having two different formulas, one for a population and one for a sample, similarly we can talk about the coefficient of variation using the appropriate symbols to represent samples and populations. We usually represent the coefficient of variation with C var, and for a sample, we have the standard deviation divided by the mean times 100% to turn it into a percentage. And for a population, we have the standard deviation divided by the mean times 100%. So essentially, the coefficient of variation is the standard deviation divided by the mean times 100%. Here's an example, some loans provided to companies in California for various projects. We have the mean amount of loans in California for the sample is 26.8 million with a standard deviation of 84.6 million. And the mean amount of loans just in Alameda County is $66.5 million with a standard deviation of $116.4 million. It says compare the variations of the two. Which group is more variable and why? Let's see how to apply the coefficient of variation in these cases. We'll do California first. Coefficient of variation is 84.6 million divided by 26.8 million. And the word million just stands for the zeros, so we can actually cross that out. And I get 3.16 times 100%, which is 316% for California. If I look at Alameda County, 116.4 million divided by 66.5 million times 100%. I get 1.75 times 100%, which will give me 175%. So if I'm comparing these, I'm really looking at, in relationship to the average, how variable is this data? And I see that because the whole state of California has a coefficient of variation of 316%. The California data is more variable than our county data because it has a higher coefficient of variation. And then one more definition for this part of our lesson, and that is the range rule of thumb. The range rule of thumb is a rough estimate for the standard deviation. That calculation is pretty complicated without technology. So if we didn't have technology at all, but we needed to calculate the standard deviation, we can estimate it using the range rule of thumb. And the range rule of thumb says that the standard deviation is approximately equal to the range divided by 4. And again, this is used to be a rough estimate of our standard deviation. If we can't calculate the standard deviation using technology, it is pretty straightforward to take the maximum minus the minimum and then divide that difference by 4. I'll talk about Chebyshev's theorem and the empirical rule in the next lesson. I want to skip over to the last page. Skipping over to the last page, there are two stocks. We have stock A at the top and stock B at the bottom. And each of these has the measures of center and measures of variation. And so the question is to analyze the stocks and draw some conclusions. What's going on here? What do you notice? What do you notice that they have in common? What do you notice that is different? One thing that you can notice right away that these two stocks have in common, their measures of center are identical. Each of the measures of center for stock A and stock B are equal. But what about the measures of variation? For the measures of variation, stock A has pretty small numbers, while stock B has some pretty large numbers. So we would say that stock B is more variable than stock A. And then the last question that I have for you, if the standard deviation of a set of data is 0, what can you conclude about the set of values? What does it mean if the standard deviation is 0? I'll let you ponder that one, and if you figure it out, stick it in your weekly wrap-up. What can you conclude about the data values if the standard deviation is 0? In our last lesson in this section, we're going to talk about 2 rules for determining where data can sit in comparison to the mean.